Hi, everybody. This is eBPF elves jumping through the windows. And I am Richard Johnson, Senior Principal Researcher for Trellix, and owner of Fuzzing.io, where I give fuzzing training as well. And just a quick shout out, I had a couple of interns help me out with this project this summer. So Casimir and Andrea, great researchers, and I'll mention them a little bit later. So our talk today is going to be about the origins and applications of the eBPF platform, and then we're going to talk about an exciting new development in that ecosystem, which is that Microsoft has recently implemented a new implementation of eBPF for the native Windows kernel side. So then we're going to go through the attack surface that's available there, the design, the architecture, the overall system, and look at the APIs and interfaces that are available. And then I'm going to show you how I went through, with the help of my interns, to fuzz kind of 4 major components of eBPF, including userland and kernel drivers. And then finally, we'll have a little wrap up. Before we get started, though, I actually promised that there would be real-time bug discovery. So one of the things that I need to start for one of the targets is right here. So I'm just going to kick that off. And we'll come back to that in a little bit. All right, so can I get a raise of hands? Who here has used eBPF or at least heard of eBPF on the Linux side? Okay, good, a nice fair number, maybe about a quarter of you. So I'm going to start off by describing in general what eBPF is, and then we're going to get to the Windows stuff. So eBPF is a virtual CPU. It's a VM in the sense of a process-based VM. And originally, the BPF was implemented as the Berkeley packet filter, designed for efficiently being able to analyze and filter packets for network observation. And eBPF takes that concept and extends it with the capability to hook APIs and have a lot more capability in also manipulating packets as well. The way the eBPF programs are written is in a native C language that then gets compiled by LLVM into a custom bytecode that is the eBPF native CPU. And then that bytecode can then be either JITted into native instructions at runtime or interpreted, depending on the mode that you execute in. Now, this code is executing in the kernel context, and so there's some security guarantees that they're trying to put around it because, at least on the Windows side, we need to sign drivers, and on the Linux side, by allowing unprivileged users to run BPF programs, they do static analysis to ensure things like this program will terminate within a reasonable amount of time, it only has so many branches, so many instructions, and so on. The original BPF actually didn't even have the concept of loops or anything like that. So execution is sandboxed and meant to be highly restricted, and it's basically giving you the same execution context, though, as a kernel driver. And it's designed for high-speed interaction and inspection with network packets and also program execution. So at this point, eBPF gives you a generic hooking framework that interfaces with uprobe, kprobe, and then also various layers of the network protocol surface. So originally, this all started to get developed in 1992, way back in the early days of the Linux kernel, and BPF itself was re-implemented on most commercial Unix operating systems as well as Linux. And at this point, there's also a userland library implementation that allows you to use this virtual CPU much like you would use Lua or perhaps V8 in a userland context. And if you've used BPF yourself, if you've used TCP dump or Wireshark and set a filter on the packets that you want to monitor, you're already using the classic BPF interface. So that was the classic BPF, and now we have what we call the extended BPF interface, or eBPF. So in 2014, Linux kernel 3.18 was released with a new system call that has a number of sub-functionalities below it, but there's a single sysBPF, and this is how you interact with the subsystem to load programs or to do various hooking and things that the BPF programs are allowed to do. And also, eBPF extended it from a 32-bit instruction set to 64-bit and expanded it with the concept of data structures, such as arrays or linked lists or hash tables that are built in. And those can be used independently and also are persistent permanently, whether or not there's a BPF program or another program attaching to it. And so there's been some red team-oriented or attack-oriented talks that use these types of techniques to leverage that for hiding data and all sorts of things like that. But the API is designed to write general-purpose programs that allow us to do things like do load balancing or sniff packets and things along those lines. And I know this screenshot's fairly small. It's not really meant for you to read it right now. It's just to show you that there's a large enumeration of sub-operations and different hook points that eBPF exposes to the user. So the actual applications and use cases for eBPF are currently, eBPF is replacing all the previous hooking subsystems such as dtrace or system tap or things along those lines. And it's got the Linux Foundation has weight behind it. There's several companies now sponsoring the development of eBPF, including Netflix and Microsoft and several others. And there are now products that you can use, such as Cilium or Falco, which are kind of Kubernetes-oriented observation platforms. There are SDKs, so you can write eBPF programs and load them using Go or C or Rust. And now at this point, there's the OS runtimes that exist both on the Linux and Windows side. So you may be encountering applications and using this stack without even realizing it. For example, Windows Defender or Microsoft Defender for Endpoint, or VMware Carbon Black, Red Canary, all these things. Even the Procmon for Linux uses this to hook all the system calls and monitor the behavior of programs. So there has been quite a bit of hype around eBPF because of the kind of emerging interest in the development of more software on top of it. So the last few years at DEF CON and Black Hat, there's been some talks like I said, focused mostly on persistence and rootkitting techniques. I also gave a talk last fall at TourCon as well as at TourCamp this year that showed all kinds of interesting tricks that allow you to subvert library loading or inject ROP payloads or migrate yourself into systemd init and things like that. So you can look up that research previously. And at the time, of course, I also was looking at the individual components and fuzzing those and just kind of exploring the whole ecosystem. And while I was doing that, after my research in the fall, I realized that Microsoft had started developing their own platform last year as well. And so it was May 21 that they released their first blog post about 2 of the eBPF hooks had been implemented. And so this is the XDP and socket bind hooks. So what this means is basically when your network card receives a packet at the very lowest layer, that's at the XDP layer. And so before the kernel is even really aware of it or before any other observation APIs can know about the reception of a packet, you have the chance to hook it. And so this has been demonstrated where they'll rewrite the headers of the packet and actually send it back out the network card before the kernel is even aware of that packet being received. And this is how they do load balancing. And so in fact, Microsoft's interest was to develop in about a year's timeline a fully working layer 4 load balancer, which ported Cilium from Linux to Windows. And so on this little chart here, I show that last year, their first implementation only had 3 APIs really available, and then in the fall, they had fairly aggressively continued to expand that until this February, where they had a minimum viable implementation that allows you to actually run real-world, useful network load balancing code on top of it. So let's talk about the Windows architecture, and this graph I'm going to end up blowing up into little components, but it's much more complicated and distributed compared to the Linux interface. The Linux interface is a single system call, and you use those sub-features to it, whereas on the Windows side, there is a user library that speaks via a local RPC to a trusted Windows service. That service is a privileged, lightweight, secure process, and so it's part of the trusted computing base, basically. What happens inside that service is the generation of the bytecode and potentially the JITting of the bytecode. So at that point, it's executing the code that will eventually run in the kernel context anyways. And then there is an ioctl based communication between that service and the kernel drivers themselves. And below that main eBPF interface, then there are shim libraries that implement the network hooks versus currently there are no program hooks on the Windows side. And in this architecture, they've actually imported 2 open source projects that I had fuzzed last fall, and that is the VM component, the userland VM that I mentioned, eBPF, and also the Prevail static verifier, which was an academic work that was trying to provide stronger security guarantees via abstract interpretation and static analysis prior to running the bytecode. So currently, the Windows implementation, as I said, is focusing primarily on the network interfaces side. Eventually, in their discussions, it sounds like they'll probably export a detours-oriented code hooking layer as well. But currently, it's being developed independently. It's not a native component. You do have to install it separately. But they say that's for serviceability reasons. So if there's any bugs, you don't want to have to wait until a patch Tuesday to protect your online Kubernetes pods or whatever. It is MIT licensed, which is nice. It's open sourced. And any third-party consumer of eBPF platform then can actually ship it as part of their product. So if you were wanting to use this on Windows, you would go and you have to turn on, you install the component and then set some BCD edit functionality. But then you get to the point where you could write a simple hello world style program that looks something like this. And it looks like normal C. It's just a function called hello that's returns an integer, takes a void context pointer, and uses an API BPF print K just to print out some text. And then you notice there's an annotation just above that function that says SEC bind. So this is telling the compiler to put this program into its own section. And in the world of BPF, a program is one function long. The functions can tail chain call into each other so you can get multiple functions working together. But a BPF program, in the context of how they treat it, is just a single function. So then you use Clang using the target BPF architecture, and it will compile like normal, and you'll end up with an ELF file on Windows that looks like this, where there is now a section called bind, and amongst other things. If you look at the text section definition there, you'll notice that it has size 0. The actual program code itself is only in the bind section. And LLVM can also, of course, dump the assembly for that. And so you can see on the right-hand column that this is using some virtual CPU instructions that you're probably not familiar with, but it's just showing the bytecode has its own language. So of course, a program typically won't be as simple as a hello world. You're going to want it to actually do something useful. And again, you don't need to read every line of code here. This is for illustrative purposes, and you can look later. But this is showing a program that actually intercepts and drops specific packets. And so in this case, there's a couple of those data structures I had mentioned, some arrays for maps. And then there is a function called drop packet that sits in the XDP section. And then that drop packet basically has access to the Ethernet header and can look to see if it's a packet that's being tracked that needs to be dropped. And so these eBPF maps, they're designed to communicate between a userland daemon that will hold like the database and do things that are more reactive because these programs are very limited. They don't really have the ability to do other I/O or things like that. They can analyze, they can modify memory, and they can write into these maps to communicate to the outside world. So the types of programs, again, XDP is that low layer one. And then there's other specific ones for if there's a socket bind call, you can specifically hook just the binds, and so you can track connections. There's various layers of when you receive or accept packets at the higher layer than XDP, various sock options. And then there's a bunch of helper APIs that allow you to enumerate the available maps or attach to a map, get a random value, various things like that. Then there's a lower level API related to those maps, and so on. And so there's maybe about 100 or so functions supporting like helper functions, and the rest you're just writing as simple walking data structures and things along those lines. Now the verifier's job is to do things like make sure you're not dereferencing pointers that you haven't checked, for example. So if you retrieve a pointer, you have to check to see if it's null before you dereference it. And most of these APIs or SDKs that allow you to write eBPF will kind of code gen a lot of that stuff for you at compile time. So ultimately, the security model that we're dealing with here is that eBPF for Windows allows you to run unsigned code in the kernel, which invalidates the driver signing enforcement that is standard whenever you run kernel code, third-party kernel code. Now, the current DACLs require administrative access to interact with any of the API layers. So really, that is the security model that we're bypassing. It's the driver signing enforcement layer that we want to get around to run our own code. And so unfortunately, you do have to be admin. On Linux, like I said, there's a limited subset of functionality that users have access to. In this case, only admin will be able to trigger these bugs. And so in a later slide, I'll show you kind of our objectives when we were looking for this in a security context. But when the bytecode's loaded, then the static verifier checks for the unsafe memory accesses and various other properties, and ultimately jits that to x64 native code. So very similar on the Linux side, it has a built-in to the kernel static verifier. On Windows, it's using the Prevail component. Again, this was an independent third-party component, and it's one of the things that I'll be fuzzing and showing bugs in a little bit. So because the Linux code was all GPL licensed, of course, this is why Windows had to have kind of a net new implementation, and which is why there's a whole bunch of new attack surface to explore. Because we've seen on the Linux side several vulnerabilities, kind of continuously coming out every 6 months or so. There's been probably a dozen of them so far. And the eBPF VM itself, as I said, I think is very interesting because I see it as a potential replacement for Lua or other userland VMs. It's very easy to work with. It's embeddable. It can run on microcontrollers. It's quite nice to use, actually. So the security guarantees that we're interested in testing from the Prevail side, or the things that Prevail is trying to ensure, is that the program needs to run in a very short amount of time, because if you're hooking every single packet coming off the wire, you don't want to introduce too much latency into a live system, especially if we're talking about something like a load balancer that's going to be dealing with a high throughput of data. And you don't want malicious programs that are loaded from third parties to be able to abuse that either. You are restricted to which memory you can read. You can't just set a pointer to an arbitrary memory address and read from it. All of this is being done as your program gets loaded from bytecode and JITted. But these are the various security guarantees. The Windows does have a mode this can run in, which actually will do the JIT itself, specifically in a HVCI or a trusted VM. That's not fully baked yet. It wasn't able to be tested. But at the end of the day, it wouldn't impact the bugs that we found anyways. So here's the attack scenarios we want. We want to see, first of all, if the administrator is loading code from a third-party project. So if I go put a GitHub project out there and I say, here's my cool eBPF filter, you could download that, and a build step could patch the resulting ELF files. Or if they took a precompiled binary, then of course there's ELF parsing issues and the loading issues, as well as the verifier itself, as it does its analysis, has potential for having vulnerabilities as well. And then once the code is loaded out of the ELF files, then it is sent via the RPC service or via the RPC API endpoints to get into the service. And so there could possibly be implementation errors in the way that you're calling the various eBPF APIs or interacting with the RPC layer. And then in the trusted service itself, that's where it's doing the JIT, and of course we know JITs can have bugs as well. And they actually include that eBPF VM both in the userland service, because in order to do the JIT in userland, it has to be able to interpret the bytecode, or you can run it in an interpreted mode, which means that the interpreter has to exist on the kernel side as well. And so it actually compiles that library for both contexts. And so you can potentially get vulnerabilities that get you into a PPL trusted service in userland, or into the kernel context based upon the interpreter layer. And then, of course, via the ioctls, which ultimately is what the service uses to communicate with the driver layer. This is where things start to get even more interesting, because at this point, ioctls are going to potentially be open to full-on native code execution. And then lastly, the shim libraries that implement the network hooks or the layer, potentially later file hooks themselves could have stateful issues or various problems as well. So this is kind of the initial attack plan. Was these are the types of bug classes we're looking for, or the areas in the code that have potential vulnerabilities. So let's first talk about the userland library that allows you to communicate with the service. So this is the library that's responsible for loading the ELF files themselves, extracting the bytecode from the various sections, assembling them, and then shipping them over to the trusted service. And there's two interfaces that's like a command line executable called BPF tool, and then there's also the built-in Windows net shell command line interface. So there's some extended commands that it adds to that. So in order to fuzz this loading, we did a combination of fuzzing on the independent open source components. So I had done that last fall anyways on the Linux. And then basically the output of that, I just simply iterated through on the Windows side to see if the code paths where I had found those bugs on the independent library were being leveraged or exposed in such a way that they would be exploitable on the Windows side. And I'll be able to show you the first bug here in just a moment. So actually the first vulnerability that I sent to Microsoft was in fact arbitrary code execution in this user library. And it was in the userland parsing of the ELF file, as you always find in new implementations. And so on the screen, what I'm showing here is that using the BPF tool, there's a subcommand saying to load a program, and then I'm supplying it with crash.o, which is my fuzzed ELF file, and telling it to load the XTP section. And on Windows, there's something called application verifier, so I turned this on, and it adds some heap sanity checking at runtime. And so again, I had fuzzed these over on Linux, and I just had a whole bunch of object files, thousands of them, and I just iterated through them in BPF tool while having a heap sanitizer basically turned on. And sure enough, as expected, there was indeed a few different crashes. This one is actually exploitable. It had to do with handling relocation sections, and as we can see here, the code that I'm dumping here is the corruption address. And so right at the location where we corrupted, of course, I put 4 A's there to indicate that I control that. And if we look at the call stack here, this is coming from a free, so I'm controlling the pointer to a free, which of course is typically considered exploitable. And that is coming from the loading of the bytecode and part of the relocation sections. This is where the buffer that was overflowed was allocated, and so it's showing that during the readelf call chain, eventually it had to parse the relocation sections into a vector of instructions, because relocations, of course, are self-modifying and they patch the code. And so this was kind of an interesting vuln and was remote code execution and got patched by Microsoft. Now, one interesting thing about the system is that the servicing model is a bit strange. I said that I had fuzzed these libraries last fall, and I found tons of crashes, and we're going to see some of them live here shortly. But I didn't want to hammer a library with just random crashes. I was waiting for a consumer application to use these libraries. And just out of coincidence, I wasn't aware when I was looking at them at the time that they would be leveraged in the Microsoft platform. So I knew that I had these on hand, but I waited. And then if you look at the eBPF for Windows repo, they tell you to submit to MSRC. However, MSRC is not releasing bulletins on this component, which doesn't necessarily ship in the box. So it's quite convoluted. In my opinion, I would just recommend submitting patches and bug reports to the individual components themselves. At this point, Microsoft has become one of the developers of those projects. Those projects only had a single developer, so I didn't want to be rude and just dump 1,000 crashes on them. All right, so that is the main bug for userland. And as I said, it's control of a free pointer. It can be exploited in practice. So moving on, the Windows service is the next component. So normally, this is the thing that's the library, after parsing that ELF file and assembling the bytecode program and performing the relocations and preparing the code blob, is ready to then be JITted or interpreted. So it sends that code over the RPC channel. And so there's an API called verify and load program. And in fact, it's the only API. So I knew that it was using RPC when I first sketched out the attack plan, and then realized that, oh, there's only one function. And so there wasn't a lot of attack surface on the RPC layer. Of course, the bytecode being curried over into the system is still going to be interpreted and JITted, and that's where the attack surface lies within this service. But basically, the library that was doing the pre-processing and loading of the bytecode was getting kind of in the way of hitting some of these same bugs that are inside the eBPF service. But ultimately, the call chain there is that the RPC API calls through a function called eBPF program load bytes, and then into the libbpf API BPF program load. So basically, the way to interpret this is that it's both accessible through the RPC endpoint, but it's also exposed through the direct eBPF API layer and can be called across programs. So basically, the service didn't really play out as far as having a direct attack. There are vulnerabilities that are in there that would have been reachable before we got them patched, but they were triggering kind of in the other components because they use the same library. So moving on to the static verifier that sits inside the service, this, as I said, was a component that's released independently. It's open source and BSD licensed, and it has a tool called check. It has a standalone verifier. So on the command line, you can run check and pass it your object file. And of course, if we do so, I will just show you a live demonstration of that one. See here. Okay. So this is the eBPF verifier code. You can go download it off of GitHub. It's the Prevail static verifier. And I've already built this, and I've instrumented the build with code coverage so that we can fuzz it right now with the AFL fuzzer. And so that check program that I mentioned is sitting right here. And it takes an ELF file in. It will tell you if it's a safe eBPF file to run, basically. So we're going to go ahead and run that, and I'm going to give it some samples here. And these are just object files that contain sample eBPF programs. They're well-formed, but we're going to fuzz them as part of our input. And this one hits really, really quickly, so we'll see in just a moment. We get crashes right away. And this is literally using stock inputs and the current build of eBPF verifier and finding crashes instantly. And this is directly exposed through the Windows surface and may eventually make its way into Linux as well. So we're finding crashes live. We could do something like so what this is going to do is give us a quick view. So we found 13,000 crashes. 30 of them were considered unique by this fuzzing tool. And if we do this, this will sort through them and run bang exploitable really quick on those and give us a quick visual of whether or not those look exploitable. It'll take just a second. So here we see there were a number of crashes. They're pretty much all null dereferences, and there's an access violation, aborts, and so on, but a good variety of crashes, and so we just found those live. So those, of course, existed within the context of Windows as well. And this is what I just kind of showed you live. OK. So Prevail, the static verifier, it's crashing. Here's one of those bugs if you pull it up in a debugger. And this one is showing one of those read AVs where the register is invalid and being offset by a large address. OK, so that's Prevail. That's a static verifier. So now eBPF, this is the VM. And we're going to be able to fuzz and find bugs in that as well. Again, this is the component that may find its way into other parts of the software ecosystem, because this could be used independently to do any sort of VM that you need. And this is just the virtual CPU. There's no helper APIs or anything like that. This just knows how to load and run native eBPF or BPF by opcodes. And that is actually the one that I kicked off earlier, because that one usually takes a little while. But sure enough, this is running, and I'll show you in a moment, but this is running the real-time fuzzing on the VM itself in the interpreted mode currently. So again, it didn't find quite as many crashes immediately, but 404 crashes, 70 of them were considered unique. And we can do something similar. Sorry, let's see. Well, the auto analysis of this one is maybe not going to happen right now, but on the slides we can see that fuzzing eBPF, you can fuzz it both in interpreted mode and JIT mode. So in the interpreted mode, this is very similar to what I just replicated live in the last how many ever minutes, half an hour. And so I found a bunch of crashes there. If you do run this output through the Bang exploitable list, you do see that a bunch of these are actually exploitable. And then, of course, if we run it in the JIT mode, it found even more crashes, and pretty much all of those are considered exploitable. So all these components, were not written with safety in mind, and they were imported into this, important Windows-level eBPF implementation. And in fact, this one is also failing on a free, and it's similar to the bug that I found on the Windows side. So this is fuzzing the components independently, and then pretty much the same bug was found in the individual library as well as in the actual existing full eBPF for Windows project. Okay, so that's all worked well. And now we can talk about the kernel layer. So in addition to the RPC service, which is or the RPC API, which is how you're supposed to interact with the kernel driver, it's supposed to go through the service. Of course, these ioctls are available directly to us, and so we can call them in whatever order with whatever parameters we want and see what we can come out with there. Now, again, just as a reminder, you do have to be administrator, and so that's the only kind of downside to the results that we had here. So there are a number of ioctl functions available. These more or less map to the BPF APIs for things like enumerating the maps that are available, loading programs, unloading them, and so on and so forth. And now we can't use a simple tool like AFL fuzz because we're fuzzing the kernel layer. So we need a new solution to do this. And early last year, there was a new fuzzer released from Overclock or Axel Souchet called WTF Fuzzer. And WTF Fuzzer is a snapshot-oriented fuzzer, and so you connect with a kernel debugger to your target operating system. You set a breakpoint at the location in which you want to start fuzzing. You step out of the breakpoint handler, and so you're right at that call to whatever API it is that you want to hit. And then you take a full memory dump. And you can then migrate that memory dump. You can either fuzz it on Windows or Linux, but you're fuzzing from a static snapshot of memory at that time. And what we wanted to do was basically send a series of ioctl requests from the ioctl handler And because it's not a live system, we had to manage that a little bit, but we have a serializable format now I'll show you that allows us to do multiple ioctl requests and hit this attack surface. And in particular, this is one of the components that Casimir helped me out with. The benefits of this is, first of all, you can fuzz with multiple cores. So you're emulating over the snapshot ultimately when you do your fuzzing. And I know it was quick on the screen there, but we were fuzzing the userland components at like 3,000 or 4,000 executions a second. You can expect to fuzz somewhere in the couple hundred executions a second per core against a standard snapshot. Now, if you're doing multiple ioctl requests like we were, those numbers come way down because you're exercising a lot more code per iteration. But long story short, it's a very reasonable, very effective, and easily scalable fuzzer that can be hosted on any environment. You don't need a hypervisor, support, or anything like that. So yeah, it's distributed cross-platform. We actually have a pull request into them right now so that you can use the QEMU GDB stub to dump a kernel image from any QEMU image. The only limits is that this uses the box CPU, so it is x64 architecture specific, but that could actually be, that's an implementation detail, right? So if you want to use a system like this, ultimately you just need to implement 2 or 3 functions. There's an initialization that allows you to just set breakpoints in the emulator itself. And so what we want to do is we want to avoid things like swapping context, because this is a static snapshot, and so we can't switch to another process because only one process is mapped in at a time. But various things that you need to do to orchestrate the execution of your program. If you needed to hook any arbitrary function to short circuit it so that you could provide arbitrary return values or anything like that, this can all be done here. And then there is an insert test case function that on every iteration, this is kind of the entry point to starting your fuzz. And this is where you would generally put fuzzy data into registers, into buffers that are pointed to by registers at your breakpoint. Or in our case, it's where we would call into our packet deserializer or our ioctl deserializer and say, okay, give me the next ioctl buffer, and then we could place it into the right locations for those APIs. So there is a demonstration harness that comes with WTF if you are interested in doing this type of fuzzing, and we forked that and turned it from a network fuzzer into an ioctl-specific fuzzer. And just by hooking kind of on the kernel API side below the device IO control file. And that looks something like this. We created a JSON format. This is what's actually written to the disk to store our fuzzy data and to be selected and mutated each time, each iteration. And these fields, like the body field there, is really an array of bytes, and that becomes the data that gets passed to your ioctl requests. And so we modeled those, couple dozen different requests that are available through the ioctl layer, and then we were able to send them in arbitrary sequence. And I'll be able to show this live in just a moment as well, but it is a little less pleasant of a UI. So what you end up having is a number of clients that are receiving fuzzy data and orchestrating back to a server. And then the clients themselves are then emulating over that snapshot and injecting the data for that iteration. And so in this case, as I said, the execution speed is quite a bit slower than hundreds. It's only a dozen or 2 executions a second, but it was indeed able to find plenty of crashes. And on the server side, there'll be one host that is then orchestrating those inputs and outputs and putting them in the right place and aggregating all that information. And what we want to see is that it will save outputs that are prepended with crash. So we did find several crashes using this technique. So let me show you that live and show you kind of what that looks like. So this is a project directory that includes the WTF fuzzer. And I don't know, I can blow it up a little bit bigger here. So this is the WTF fuzzer. It's just compiled as a static executable. It is going to collect code coverage that is the aggregates, and then each iteration, it's going to send a sequence of ioctls based upon our JSON template, and then continue to collect that. Our inputs For the demo, I'm only going to use one of the templates, but we modeled. We modeled a series of these requests. So, to create an array map or create a program and then get program info, or to, pin programs to memory and so on and so forth, using those various APIs. And as I said, this is what it kind of looks like and as it's persisted to disk. And each iteration, this is showing a sequence of 3 or 4 ioctls. And those will get mutated and end up looking something like one of these guys. It's not as readable, obviously, but as it generates new data and gets new code coverage, reserializes out back to our JSON format. And then the way that I run this is through a little script here. Maybe I'll pull it up and basically it's just tell it how many cores you want it to spin up. It'll spin those up in screen behind the scenes, and it's going to run htop so we can make sure that they're all connecting and getting going. There's a number of parameters to WTF that we don't have time to go into, but this sets things like how many attempts to run. So this will run 1 million iterations. How many instructions to limit per iteration. So this is another way to intentionally short circuit the execution so it doesn't get into areas of code that would cause invalid crashes and things along those lines. This is running in the emulated mode of the box CPU. WTF does support running on top of KVM hypervisor as well as the Windows hypervisor platform, and so on and so forth. So So I'm going to run it with 8 cores, and I'm going to tell it to use our ioctl fuzzer mode. And so I'm telling it not to copy previous output. Start with an empty input queue. So no. So this is just going to spin up 8 cores. Those are going to be connecting back to the server, so we can inspect this in real time. All right, and so here's our server. It's receiving data from the various cores, and what we're looking for is, yes, it has already found a number of crashes just almost immediately based upon that single definition. Now, the definitions we have in there are not already set up to trigger crashes. These are just standard ioctl requests, and just simple mutation on them was able to find a bunch of bugs. And there's a way to replay those and stuff, but it's a little time intensive, so I'll just kind of show you the results. So we did find a number of vulnerabilities in the driver layer. Now, again, unfortunately, these you do have to be administrator to hit these. So I would call most of these, resiliency bugs, or they're not exploitable code execution bugs so far. We reported one to Microsoft that should have been, but due to the way that some of the ioctl buffering was set up, it didn't work out. But we did find read AVs in the Murmur 3 implementation. You can look at these call stacks later. Null pointer references and the eBPF destroy. This is the same bug that I showed a few slides back when it was doing a free on the eBPF destroy. So you can hit it from the kernel context as well as from the user context. Trampoline table crash, another null D reference. And besides these crashes, and here's an example, how complicated these serialized packet structures end up looking. They're sending, this one, it looks like it's sending about 10 different ioctl requests. So it is getting deep into these APIs. And then, of course, beyond WTF, the new kind of fuzzer that is really exciting and interesting for doing full system fuzzing is called NIX, or KAFL. And it's a hypervisor level fuzzer that allows you to do equivalent style of fuzzing, but on a live running system using incremental snapshots. And so, of course, we wired that up as well. And we did find a number of bugs using that approach, but they were more or less duplicates of the bugs I just showed. One thing that's not in the slides that is still interesting is that beyond these crashes and the exploitable bug that I showed earlier, there's also the ability to manipulate these maps. And not only are they useful for persisting data arbitrarily, maybe hiding data in places where people won't be looking, but they're also able to do arbitrary control of the non-paged pool. And so if you are exploiting a kernel bug and perhaps you're doing it to bypass DSE, if you have administrative privileges, you could run this code, use the map control APIs, and do arbitrary layouts of your non-paged pool, basically, to assist with exploiting other bugs. So that's the main eBPF core.sys. And then lastly, there are the extension modules, which is where the network implementation of the hooks live. And in this case, the code was a bit more difficult to fuzz. We didn't really want to send packets fully from the outside world into the kernel in the way that we were fuzzing. And so I more or less did a manual code review of this. It's only about 20,000 lines of code or something. And ultimately, it's really lightweight shims around your already existing network APIs. And there wasn't hardly any memory management. It's all zero copy type stuff. So did not actually find any vulnerabilities in the code that I looked at, which was the XTP, bind, and cgroup hooks. But what I'm looking forward to, or I'm really hoping that Microsoft implements, is the code hooking layer, because that becomes interesting for many, many reasons. There isn't a nice native built-in shim. Well, Windows has many different ways to do shimming, but oftentimes you have to fully implement a library's public interfaces in order to use them, or there's all kinds of rough edges. It would be very nice if the eBPF Windows side does allow us to access detour-style hooks through the eBPF VM. So I'm looking forward to that. I'm hoping that's coming around in the future. And then finally, some concluding thoughts is basically eBPF is dominating the world of doing network telemetry. And so this is currently a new technology, basically. On the Windows side, it's all net new. And when we did this work kind of ahead of the curve, it's not really being used yet. It's just now in its first viable implementation. And I wanted to do this proactively so that we could patch up these bugs, point out where the problems are. And now if you look in the Windows GitHub, they're writing fuzzers and they're doing work in this direction now that they see people from the security community are paying attention. And obviously if this is being used as an underlying tech in all the network monitoring and telemetry out there, then we need this to be secure. Yeah, and so the results were ultimately one very critical remote code execution bug that would give you administrative privileges, a number of bugs that can tear down a system, and then arbitrary kernel pool control that would allow you to assist with exploiting other bugs. And yeah, so that's about it. Trellix is employing me to do this type of research, so keep an eye out for my next work. And I've been Richard Johnson. Thank you.
Okay, thank you very much, Richard. First of all, it's 2022. Were you surprised that when launching new features that they weren't fuzz tested before by the vendor, and that you're still finding RCE bugs in new products 2022?
Yeah, obviously they were focused primarily on just getting functionality put together, but once I realized that they were using these third-party components and hadn't done any security testing with them, this is a problem that everybody faces. Whenever you import third-party code into your code base, you need to take ownership over that in some way. You have some responsibility to make sure it's secure before you go ship it as part of your platform. So, that's basically the opportunity that I saw, and I just assumed that, already knowing that there was some potential there, that it would pay off in the long run.
Okay, the VTF fuzzer and the future of that. This was like a use case, more showcasing the fuzzer, what was the egg and what was the hen?
Well, I think anybody who's paid attention to fuzzing the past 5 years, you will be aware of AFL fuzzer and libfuzzer, which is built into LLVM compiler. But those are only allowing us to test user code, right? And so until recently, there hasn't been a very good code coverage-driven fuzzer for the kernel side that works on cross-platform. and it's scalable, and it's very, very easy to set up. Like, I can go from being in a debugger and a half an hour later have a fully working fuzzer, so it's very agile. So yeah, a little bit of awareness in here. Overclock's a friend of mine, and trying to show people the potential and unlock capabilities for everybody to go out and test new attack surface and find good bugs.
Okay, thank you very much.
Thank you.
Do we have any more questions from the audience? Oh, there is one there.
Is Linux and Windows eBPF bug compatible, so to speak? Have you found similar problems, or are they completely different?
So not vulnerability-wise, because it is separate code, but what is interesting about eBPF is that the programs written in that VM language are cross-compatible. So I do actually have a talk coming up at HushCon this December, where I will be talking about a new offensive rootkit that is cross-platform and some things like that implements some of the modern techniques that the media is getting really hyped about because they're seeing it in active campaigns. And I'm going to show basically what the next gen is going to look like and build awareness around the fact that, okay, these rootkits are now going to be portable. There's actually interest. I gave this talk at Black Hat, and there was somebody from Apple who came up and was asking me questions, which is interesting. I hadn't heard until maybe that point that Apple would be interested in their own eBPF stack, perhaps. So yeah, it's an exciting space.
Okay, one more question. Is there something that the eBPF on Windows have added they can't do on the Linux version when they adopted it, or is it exactly the same?
No, yeah, so far it's a more limited implementation that just does the network side. But of course, again, the code is different, so the architecture is separate and all this and that. The one thing that they're trying to do is they're trying to figure out how to build a layer into this that if there are vulnerabilities, then they won't matter, like by isolating it in the HVCI. But I think that progress is stalled, and I don't think it would succeed fully in what they're intending, because you can bypass that by just speaking to the ioctls directly.
Okay, thank you very much. Now we have a coffee break for 30 minutes, a bit plus 30 minutes. So we resume a 3:45 here for the next talk. So a big round of applause. Thank you very much.